All right, hello everybody. So what we're going to do here in this first lesson of our new unit, which is going to be a unit that we're going to carry on really till the end of the semester, is evolve and refine an idea that we've been working on since the beginning of the semester, the beginning of the year, which is how do you prove things in geometry actually are what think they are, and not just have to logically argue it because it seems that way to us. And so the previous step in this journey was using transformations to do this, and we ran into some issues, we ran into some difficulties with the complexity of that. But this evolve idea, I think, will prove to be a little bit more useful than just transformations. But anyway, let's get into this. So certainly take an opportunity to pause this video, set up your Cornell notes if that's how you're planning to take these notes as we get into this. I'm also going to try to cut this into 3 or 4 different smaller segments, at the end of which you can take a moment and kind of summarize the notes you've taken up to that point, take a little mental break before moving on to the next part. Okay, so here we go. So the purpose of our discussion today is for us to talk about how we can tell two figures, in this case for the most part triangles, are congruent or similar without the use of transformations. So let's talk about congruency and similarity, both in the context of transformations and outside the context of transformations. And so congruency is the one that we've dealt with probably the most, and you've dealt with the most as a math student. But keep in mind, congruency, we're just talking about rigid transformations. That's it, and that's a term we should be well attuned to, since we've been using rigid transformations really for the better part of a month or so. Now, when we talk rigid transformations, we are talking about 3 specific types of transformations: translations, reflections, and rotations. These are one and the same. This is a complete list of rigid transformations, and keep in mind we call it rigid because they can move the shape without changing the components. Now, for clarity's sake, when I talk about components, I'm talking specifically about the components of the shape. In this case, we're talking about both angles, and we're also talking about sides. And so don't get confused by the terminology. Components just refers to the pieces of the shape, in this case angles and sides. And so we know with rigid transformations, if you translate, reflect, or rotate, the shape itself will maintain its same size, ergo angles and sides do not actually change. And so like the big takeaway here is that the pre-image and the image will remain congruent. And if you want, and this is probably a good idea for notes, so we can throw in kind of like a quick visual example. So in other words, in congruency transformations, rigid transformations, we kind of consider the entire triangle, and that entire triangle may flip and rotate and translate, but in the end, the triangles themselves, the pre-image and the image, will remain actually congruent. And we can remind ourselves the congruency symbol is that equal sign with like that squiggly or tilde above it. We can say this image and pre-image are congruent as long as we're using rigid transformations. Now, similarity is a term that I'm certain you guys have heard before. If not, it's not a big deal. We just have to associate similarity to non-rigid transformations. So unlike the ones above that are going to keep the same shape, no matter how you move it through a translation, reflection, rotation, non-rigid transformations are exclusively, at least for us right now, and you'll add more later in your math career, but for right now, non-rigid transformations, we're referring to dilations. And keep in mind, dilations mean that we're scaling the shape in terms of its side lengths. Now again, just for clarity's sake, when we're talking about scaling, we're talking about multiplying by a k-factor. Okay? Now the term k-factor and the term factor and the term scale all basically mean the same thing. Now the idea of scaling is it happens just for the side lengths, and so we know we're going to have congruent angles. Has congruent angles right here. Where's my highlighter? There it is. Congruent angles. And we have sides that will not be the same length, but will be reasonably scaled. And so in terms of like a picture, like if I have a triangle and I want to dilate it, I'll end up with a much larger triangle in which all the sides are in the same ratio, and the k-factor is how we control those side lengths, but the angles themselves are going to be congruent. Okay, and so the big question from this set of notes, what we just attempted to answer, was what does it actually mean to be congruent and similar associated with transformations? Now, similarity, we should also note, has a symbol, and we'll talk about this more later, but in terms of similarity, we're actually just going to use a single squiggle. And so you might notice that symbol is also in the congruency symbol above the equality, but for similarity, that's going to be our symbol that we'll use, and we'll see it again in the near future. Right? And so if this is our starting point, we have these transformations which ultimately did actually prove congruency. We should probably talk for a minute about how these actually prove these things to be congruent or prove these triangles to be similar. This is a very kind of obscure point, and this is one that a lot of your peers, and frankly a lot of my peers, kind of miss in terms of how transformations actually prove things are going to be congruent or similar. But if you consider the test he just took, and you consider the biggest component of that test was mapping series of transformations, then it should become no surprise that what we're really talking about are series of transformations. So consider this scenario. We have one triangle, the pre-image, which I'll label here as a PI, and we have this other triangle over here that's the image. Well, if I can show you how to go from the pre-image to the image by using just translations, reflections, and rotations, then we can certainly conclude that the pre-image and the image must be congruent. So like for example, if I take this, I'm just going to do a really quick one here. If I take this and I translate it up along this vector, and of course everything has to kind of move along the same vector, and so the triangle is currently here. Okay, and then I take a rotation around this point. So I'm going to rotate down until the triangle is here, and then I'll do a quick reflection along this line, and I can show that the pre-image and the image triangles will lay one on top of the other, and we can conclude those triangles had to be congruent because we just use rigid transformations. And that was really kind of the weird point I was trying to make with most of this stuff in this unit, that if you just use rigid transformations, the pre-image and image should remain the same size. Same angles, and of course same side lengths. Same is true for similarity transformations or dilations, excuse me. If the pre-image maps to the image by a series of rigid transformations and at least, and here's really the key phrasing here, at least one dilation, then we can certainly conclude the triangles must be similar. Because if you're moving them just by rigid transformations, nothing changes, but then you include a dilation, well, the angle should stay the same, but the side length should scale in a certain way. And so if we had these two triangles, and again, we'll label this one kind of like the pre-image, and this one is the image, and I can show how to go from one triangle to the next by a series of transformations. Like for example, if I take first this vector to translate this triangle here, let me just get this third vector in. Okay, thus my new triangle is kind of like in this position. And then I can show you that I'm going to rotate around this point, okay, counterclockwise, probably about 90 degrees, which will put my triangle here. And then adding what we know about dilations, dilating back to this point by some k factor, I'll end up with a triangle in this position. And so again, if we can show that these triangles move either just by rigid transformations, meaning they're going to end up congruent, or by rigid transformations and a dilation, we can claim that they're similar. Okay? And so I'm going to pause the video here. This will be the end of the first part. And so you might want to take like a beat, consider the notes we've taken up to this point, and maybe if you have some space like right here, or maybe in this blank spot, you can write like a quick summary of what we talked about so far. That's a really good tactic while you're taking notes to stop every like 10 or so minutes. Even if the teacher doesn't give you, or I don't give you that time to do it, like taking a beat and just like summarizing, doing a like a quick summary. Is a way that can help you kind of retain that information better. So go back, I would suggest go back and reread your essential question, reread through these notes, or maybe even watch these parts of the video again, and ask yourself, what was a big takeaway from this part of the notes? Okay? If you do that, you're going to become a more effective note taker, and this information might become a little easier. So this is part one. I'll be right back to you in part two.